simulator. All right, so I've got a D flip-flop here, right, from the library. Right? If you go to insert symbol and type DFF, you get this particular D flip-flop. It has then the input D. It also has, actually, maybe I can zoom a little bit more here. Sorry. All right, D flip-flop, input D. This triangle is the clock input. Remember, these are clock edge trigger devices. This is a rising edge trigger device. That's what this triangle means. Here's your clock. It's a rising edge trigger. There are two other inputs that I don't have connected. This PRN is a preset, which would cause the output Q to always be a 1 when we assert the signal. The CLRN is a reset, which would cause Q to always be a 0 when we reset it. These are, I won't talk about them anymore. I don't want to bring those into this. We just want to look at the basic D flip-flop behavior, right? We don't have to connect everything to the flip-flop in order to get it to work. And so you can see I've got these two inputs, pins D and CLK stands for clock, and we've got our output Q. Right, I already ran analysis and synthesis on this particular circuit. Right, I've got the simulation waveform. We're going to then, I'm going to go ahead and run this so we can see the output and see how this changes. Right, so this is our D flip-flop, right? We've got our clock, we've got our input D and our output Q. All right, so remember this is a rising edge triggered. So we'll only be on the rising edge when we get a change, possibly get a change in our output. So here we can see the Q started off as a 0. And what I did here is I clicked on clock. You can click on these arrows here and get then this little pointer to go to the next time step, right, the next clock edge. All right. So here we can see at 2.5 nanoseconds, we have a rising clock edge. Right? By that rising edge, we mean that the signal level is transitioning from a 0 to a 1. So it's rising from 0 to 1. And this flip-flop is positive clock edge triggered or rising clock edge triggered. They both mean the same thing. Right? At this time, D is a 0. So that means Q will be a 0. Right? And Q will hold its value until the next clock edge. The next rising clock edge. So at the falling clock edge, there's no change. It's the next rising clock edge that the circuitry would say, okay, what's the input of D? Well, D is a 0, so Q will be a 0. And then at our next rising clock edge, well, in this case, D is a 1. So now we can see the output Q becomes 1. Q is equal to D. As we go across here, our next rising clock edge, D is still a 1, so Q remains a 1. In between, Q does not change its value, right? Q can only possibly change its value on the rising clock edge, right? Q holds its value. Next rising clock edge, well, D is a 0, so we can see that Q transitions from 1 to 0 in this case. And then it's going to hold its value, right? At this, as we go across, Q remains 0. Next rising clock edge, because D is a 0, Q is a 0. Right, Q holds its value. Next rising clock edge, D is a 0, Q remains a 0. Finally, next rising clock edge, D is a 1, so Q becomes 1. Q holds its value. Next rising clock edge, D is still a 1. Q becomes Q stays a 1. Right. You can see here, right, when D transitioned from 1 to 0, there's no change in the output Q. That can't possibly happen until we get to the next clock edge. Right. Next rising clock edge. So next rising clock edge, D is a 0, Q transitions. Right. So there's an example then of how the D flip-flop works with a functional simulation. Right. Right. Our next flip-flop is the JK. So let me go ahead and make the JK the top level. Let's run analysis and synthesis. All right. What I should mention here is I just went ahead and used the text editor to just go ahead and put in a note here The other thing we did with the flip-flops in lecture was we derived their characteristic equation. So we said Q next is equal to D. Right here, the JK flip-flop characteristic equation, Q next is equal to J, and it with K naught, or with K naught, and with Q. We're going to use these when we get to the next lecture on excitation tables. So I've just included them in here as a reminder of what we derived. For JK here, I also tried to put a reminder of how the JK flip-flop works. Right, when JK is 0, 0, we have the hold state. Let's run the simulation. So let's open up this simulation. Let's run this first case. All right. Let's take a look at what happens. Again, I should mention, right, is this JK flip-flop, right? It has the inputs J and K. It has the clock input. The triangle is the clock. It's a rising edge triggered clock, right? We don't have anything hooked up to the preset and the reset. And here's our output. All right. So let's take a look, right? I've highlighted the clock. I'm going to click on this. We're going to get to our first rising clock edge. Well, our first rising clock edge, J is a 0 and K is a 0. That means Q is going to hold its state. It won't change. So Q is a 0 before this. Q is a 0 right now. It maintains its state. And let's go to the next rising clock edge. Right? At the next rising clock edge, J and K are still zeros. No change in Q. Right? Next rising clock edge, same thing. They're both zeros. No change in Q. Same thing here. J and K are both zeros. No change in Q. But now at our next rising clock edge, J is a 1 and K is a 0. This is the set state. And so we can see now that the output of Q becomes a 1. Right. Next rising clock edge, J is still a 1, K is still a 0. So our output Q is still a 1. We're going to see, right, next rising clock edge, that's the same thing. There it's the same thing. Now at this clock edge, J is a 0 and K is a 0. We said that means Q will hold its state. So Q state before this was a 1, Q will hold its state. And we can see all the way across here, as J and K remain 0, Q remains 1. And we get back here, well, J is 1 again, and K is 0, so it's still going to maintain that set state. All right, let's change our simulation waveform a bit. All right. So here I was using a 10 nanosecond. Oh, sorry. Here, actually, I'm just going to click on. I'm going to make J 0 the entire time, and let's just make K 1. Let's maybe offset this by actually. So K is going to transition between 1 and 0 here. Actually, what we're going to see is that our Q, well, let's run the simulation. Save it. So we can see the results before I start talking about them. All right, so what I was going to say is we're going to see that Q is always going to be 0 here with this particular combination. All right. So here, let's look at our clock. Right. Our first rising clock edge, J and K are both 0. So Q maintains its state. Its state happened to be a 0. And so it maintains that state. We're going to go across. We're going to see that when K is a 0 and J is a 1, well, the output Q should be a 0. Right? So it is a 0. And K will just always reset this to 0. Now, because in this example, right, it's either going to hold state or reset it back to 0. Q will be a 0 all the way across here. Let's change our waveform a bit here. Okay. All right. Let's go ahead and run this simulation. All right, now let's take a look at what's going on. So remember, our transition is only on rising clock edges. Let's go to the first clock edge here. Well, the first clock edge, J and K are both zeros. Q remains a 0. Next clock edge, same thing. J and K are both zeros. Hold state. Q retains its state of 0. Next rising clock edge, K is a 1, J is a 0. Well, that's the reset state. So Q becomes 0. Even though it was already 0, it becomes 0. Had it been 1, it would transition to 0 at this point. Let's go here. Next rising clock edge. All right, next rising clock edge, J and K are both 1s. That's the toggle state. Since Q was a 0 in the previous state, we could see that Q now toggles to 1. Right. Next rising clock edge, K is a 0, J is a 1. That's the set state, so Q remains a 1. Next rising clock edge, same thing. J is a 1, K is a 0. That's the set state. Right. Next rising clock edge, K is a 1, J is a 0. That's the reset state. So Q changes from 1 to 0. The output Q becomes 0, right, for the reset. Next rising clock edge, we still have the same combination. K is 1, J is 0, Q remains 0. Right? Or Q is reset to 0. Here, then J and K are both zeros. Next rising clock edge, Q holds its state. Q is a 0, Q remains a 0. Next rising clock edge, J is a 1, K is a 0. That's the set state. So Q becomes a 1. Next rising clock edge, we have J and K both 1s. That's the toggle state. Previous to this, right, Q was a 1. It toggles now to 0. Right. Next rising clock edge, J and K are both 1s. Q toggles, so since Q is a 0, Q now becomes a 1. Next rising clock edge, J and K are both zeros. We hold state. Q is a 1, it stays a 1. Same thing there, it holds state. Same. Now here, K is a 1, J is a 0. We have the reset condition. In this case, then K actually causes the reset. Q goes from 1 to 0. All right. So by playing with these waveforms a bit, generating some of these different combinations, you can then see how the JK flip-flop works. All right, our last one we're going to take a look at then is the T flip-flop. Let me set this as the top level while we talk, run analysis and synthesis. All right, so T, remember, is the toggle. All right, when T is 0, it holds state. Right, and so I've got the characteristic equation here, which will be important, like I said, in our next lecture. But what we remember from the T flip-flop is whenever T is a 1, the output Q toggles. When T is a 0, Q doesn't change. Now let's take a look at that simulation. All right, so here's our clock. All right, it is a rising clock edge triggered flip-flop. Now Q is a 0, T is a 0. That means hold state. That means Q doesn't change. So we can see that Q did not change at this time. Next rising clock edge, T is a 1. That means we toggle. Toggle is a complement. So Q is a 0, Q now becomes a 1. Next rising clock edge, T is a 1. That means we toggle. Q is a 1, Q now toggles to 0. Next rising clock edge, T is a 0, so we hold our state, meaning if Q is a 0 before, Q is still a 0. Next rising clock edge, T is, Oh, I caught a state transition here. Okay, so this clock edge, T is a 0. Right, Q retained its state. I have something bad in my simulation here. At this clock edge, it looks like T is transitioning. So we don't know exactly where this was sampled, but we're going to say T was a 1 when this decision was made, because we can see that Q actually toggled. So I've not set up the simulation the best way, because we try not to have these overlapping or these states changing at the same time. So the idea is you don't want your input state T to change at the same time you have a clock edge. So that's why we had that behavior here. Let's go here where we have this rising edge. T is definitely a 1. Q was a 1. It toggles back to 0. Next rising edge, T is a 0. We hold state. So Q is a 0. It retains its state. Next rising clock edge, same thing. T is a 0. We hold state. So you can play with these waveforms a bit, right, to get this to toggle more consistently if you want, or to see it holding state when Q is a 1. But now you have, hopefully you have a general idea of how these flip-flops work. What I would definitely encourage you to do is to draw these circuits, right, in Quartus, run the functional simulation, work with a simulator, see how they work, right? We will start using the simulator, well, we will use the simulator in homework with some of these upcoming circuits. So you want to make sure you're familiar with that. All right, thanks for watching. Hope you have a better idea of how to work with these flip-flops in Quartus and run the simulator.